Hello everyone. In this module, we're going to be learning about the EKG or ECG or electrocardiogram. EKG is a line graph that records the electrical activity of the heart over time. So in order to understand EKG, we need to know how electrical signals move through the heart under normal conditions. Normally, SA node located at the wall of the right atrium acts as a pacemaker. So it depolarizes to send waves of depolarization to myocytes of right and left atrium. From there, depolarization funnels through the AV node and goes to his bundle of branches, and finally to the Purkinje fibers. The Purkinje fibers are embedded in the left and right ventricles. So their depolarization will cause ventricular contraction. Here we'll look side by side how EKG reads the electrical activity as it moves through the heart. EKG picks up electrical activity and plots it against time. So time is always on the x-axis and y-axis is the electrical activity. So if there is an electrical event occurring in the heart, there will be either positive deflection or a negative deflection in the EKG. Positive deflection is when the graph moves upward and negative is when it moves downward. Looking at this normal EKG, P wave is the first electrical event in the cardiac cycle we see here. It represents atrial depolarization. Next we see is QRS complex, which represents ventricular depolarization. But before this, we see a flat line in between, which is a PR interval. And this is here because it takes time for the electrical signals to move from atrium through the AV node, his bundle branches, Purkinje fibers before finally reaching the ventricles. QRS complex is the largest section in the EKG. It can include a negative deflection called Q wave, a positive deflection R wave, and again a negative deflection S wave. Following QRS complex, we see another positive deflection called T wave, which represents ventricular repolarization. We do not see a graph for atrial repolarization because it takes place at the same time with the ventricular depolarization. So the QRS complex masks atrial repolarization. Here is a normal 12 lead EKG. 12 lead because there is 12 different recordings of the heart's electrical activity. We have lead 1, 2 and 3 on the left side. Then we have lead AVR, AVL and AVF. These 6 leads are also called limb leads. Then we have lead V1, V2, V3, V4, V5 and V6, which are also called chest leads or precordial leads. On the bottom of the EKG, usually 1 or 2 recordings of multiple QRS complexes are shown. These are called rhythm strips. These help us to better determine the heart rate and rhythm. I have zoomed in lead 2 on top of the screen so we can see that it contains the P wave, QRS complex and the T wave, just like I explained before. It's very easy to understand what each of these waves represent in an EKG, but the trickiest part to understand is what each of these leads in a surface EKG represent. If you see carefully, you will notice that all the QRS complexes in lead 2 are pointing upward. Then on lead AVR, all QRS complexes are pointing downward. And on lead V3, QRS complexes are pointing slightly upward and slightly downward. All of these EKG leads are recording depolarization of the same heart, but all of them are showing different recordings. This is what we need to understand, and that is what we're going to talk about next. When the electrical impulse generated from SA node reaches to the ventricles, these electrical signals move to different directions in the myocytes. Some will move this way to depolarize the left ventricle and some will move this way to depolarize right ventricle. But if we sum up all these, then we will get a summation vector that looks like this. So each of the EKG leads will look at this summation vector from a different point of view. So each EKG leads will show QRS complex, which represents ventricular depolarization, as a different shape because they are looking at a same summation vector from a different vantage point. To make it easier to understand, Let's say a car is moving from point A to point B. There are two persons, one on point A and another on point B. Both of them are observing the same car. The guy on point A will say that the car is moving away from him, but the guy on point B will say that the car is moving towards him. Both of them are correct because they are looking at the same car but from a different vantage point. That's the same case with the EKG leads. All of them are looking at the electrical activity of the same heart from different positions, so the shape of the waves will be different in all of them. Here in this picture I have shown the heart with its summation vector, and I have also included all the ECG leads with their vantage points. Let's see if we can make sense of it now. Lead AVR is viewing electrical activity on the heart from the right side. So all the electrical activities are moving away from it. And when electrical signals move away from our EKG lead, it generates a negative deflection on the EKG. Contrast to this, lead 1 and lead AVL views the electrical activity of the heart from the left side. So the electrical signals are moving towards them, hence there will be a positive deflection in these leads. Lead 2, 3 and AVF are viewing from the inferior part of the heart, and the chest leads are viewing across the heart with lead V1 being more on the right side. So now let's see at this 12 lead EKG and see if we can make sense of it. In lead AVR, QRS complex is going downward because it views the heart from the right side and it sees the electrical activity going away from it. Lead V6 lies on the left side and sees all the electrical activities moving towards it. Hence, all the QRS complexes are going upward. Lead V3 is in the middle, hence some part of the QRS complex are going upward and some are going downward. So all these EKG leads are looking at the same electrical activity on the heart, but they all look different because all of them view the heart from a different vantage point. Now let's briefly discuss the cardiac pacemakers. SA node is the most dominant pacemaker of the heart and maintains a heart rate of 60 to 100 beats per minute. Other pacemakers also exist in the heart, but all of them are slower as compared to SA node. And if SA node fails, others take over. AV node can act as a pacemaker but has a slower heart rate of 40 to 60 beats per minute. Similarly, his bundle branches, and Purkinje fibers can also act as a pacemaker, but these have even slower heart rate of 25 to 40 beats per minute. Conduction velocity is the speed at which the electrical signals move through the heart. Purkinje fibers have fastest conduction velocity and AV node has slowest conduction velocity. Conduction velocity being slowest in the AV node is very important because it buys time for the ventricles to fill with blood. And if we go back to this picture, the PR interval was because the electrical signals has to travel through AV node, his bundle branches and Purkinje fibers before finally reaching the ventricles and depolarizing them. Most of the part of the PR interval is due to AV node because it is where the conduction velocity is slowest. So that's it for ECG part 1. In the next video, we'll learn how to determine the heart rate from the ECG, and also we'll learn about the ECG axis and how to determine it from the ECG. Thank you.